Let's take a look at this differential equation. 4xy double prime plus 3y prime minus 3y equals 0. First, we're going to show that x equals 0 is a regular singular point. First, to show that it's a singular point, let's take the whole thing and divide by 4x. So we get y double prime plus 3 over 4x y prime minus 3 over 4x times y equals 0. Clearly, this is undefined at x equals 0. So that shows that it's a singular point. However, it's a special type of singular point called a regular singular point. There's a couple of ways of showing this. The way that I will do this is as follows. So let's go back to the original differential equation, 4xy double prime plus 3y prime minus 3y equals 0. Let's figure out a couple of limits. Let's figure out p sub 0, which equals the limit as x goes to 0 of, we'll take the 3 here, divided by 4x, and then let's multiply it by an extra x. Okay, so that's equivalent to taking the 3 over 4x that I saw here and then multiplying it by an extra x. Okay, so this works out, of course, to be the limit as x goes to 0 of 3/4, which is just 3/4. So that has a limit. That limit is defined. Let's also do the same thing for this part. So we take the limit as x goes to 0 of negative 3 over 4x, so negative 3 divided by 4x, equivalently the negative 3 over 4x that I saw here. And this time let's multiply it by an extra x squared. This is the limit as x goes to 0 of negative 3/4 x, and that's 0. So both of these limits exist, and therefore it is a regular singular point. So that checks that x equals 0 is a regular singular point. To find the two roots of the initial equation, there's a couple ways of doing this. The easy way is as follows, that we set up the equation r times r minus 1 plus 3/4, this 3/4 that I see here, times r, plus the 0 that I see here equals 0, and solve for r. So that gives r squared minus r plus 3/4 r equals 0. So r squared minus 1/4 r equals 0. And so that gives that r times r minus 1/4 equals 0. And so I get my two solutions of the initial equation, r equals 0 and r is equal to 1/4. These are separated by an integer, and so the techniques that I will use are I'm sorry, I said that wrong. These are not separated by an integer. They're separated by 1/4. And so the technique that I'll use will result in two different solutions. Okay, let's now go out of order. So we've done part 1. We've done part 2. Based on the differential equation, what is the minimum radius of convergence for the power series? So here's our differential equation, 4xy double prime plus 3y prime minus 3y equals 0. Let's rewrite this as x squared times y double prime plus x, so I'm multiplying by an extra x over 4 to make that happen. Multiplied by x over 4 gives 3/4 times y prime. Then if I multiply by x squared, it gives minus x squared over 4, it gives plus negative 3x squared over 4 times y equals 0. So I've rewritten this differential equation multiplying by x over 4 to write it in this way. So I have an x squared y double prime up front. Then I pulled this x out here, and then I have this. All right, we now take a look at the things that I have put in parentheses. So in parentheses I have 3/4 and negative 3x squared over 4. Those functions are perfectly well defined. There's no places where if I plug in a number, it blows up. And so based on number 5, the minus radius convergence is going to be infinity, because the terms that I have here in parentheses, I have no singularities. There's no place where I get into trouble when I plug in x. And so the minimum radius of convergence is going to be infinity. Okay, so that's part 5. Okay, now the hard work. Let's now take a look at the recurrence relationship for the coefficients. Okay, now to find the recurrence relationship for the coefficients, let's start with a fresh sheet of paper. So 4x squared, 4xy double prime plus 3y prime minus 3y equals 0. And our guess for the solution is going to look like this. Y is equal to summation n equals 0 to infinity a sub n x to the n plus r, where r is going to be either 0 or 1/4. I could write it 0 and then 1/4 and do it twice. It's usually a little bit less work to write it like this and then plug in later. Y prime is going to be equal to summation n equals 0 to infinity of n plus r a sub n x to the n plus r minus 1. And then if I shift the index, I get summation n equals -1 to infinity of n plus 1 plus r a sub n plus 1 x to the n plus r. Now notice, because I have an n plus r here, not n, I have the index shifts to n equals -1. Y double prime is going to be equal to summation n equals 0 to infinity of n plus r minus 1 times a sub n x to the n plus r minus 2. Then I need to multiply that by 4x, so 4xy double prime equals summation n equals 0 to infinity. I get 4 n plus r minus 1 a sub n x to the n plus r minus 1. Okay, now I shift the index, so this is going to go from -1 to infinity of 4 n plus 1 plus r n plus r a sub n plus 1 x to the n plus r. Okay, so let's add these three things together. So 4xy double prime plus 3y prime minus 3y equals... Okay, first let me deal with the -1 bit. Okay, so if I plug in n equals -1 into this equation, I'll get 4 times r minus 1 a sub 1, or sorry, a sub 0 times x to the r minus 1. Then if I plug in, if I look at the n minus 1 term over here, if n equals -1, then I have r a sub 0 x to the r minus 1. So that's the special case of -1. And then I have summation n equals 0 to infinity of this part, 4n plus 1 plus r times n plus r a sub n plus 1, then plus 3 of these, n plus 1 plus r a sub n plus 1, then minus 3 of this, so 3a sub n x to the n plus r. And this is supposed to be equal to 0. So if I set this equal to 0, looking at this first part, I get that 4r times r minus 1 plus r times a sub 0 equals 0. And so that means that 4r squared minus 4r plus r, and I forgot the 3 here, I apologize, there should be 3 there, so 3 there, plus 3r equals 0, so 4r squared minus r equals 0, r times 4r minus 1 equals 0, and lo and behold, I get the same solutions that I had before, r equals 0 and r equals 1/4. What I did here is not technically necessary. I had done this earlier at this step when I solved the initial equation, got r equals 0 and r equals 1/4. This is just a useful double check to make sure that I didn't make a dumb mistake with the arithmetic. So I should get the same answers that I had before. So r equals 0 and r equals 1/4. Those are my two possibilities. Now looking at this part, I get that 4 times n plus 1 plus r times n plus r. Then I have another thing that has a sub n plus 1 plus 3 n plus 1 plus r. A sub n plus 1 minus 3a sub n is supposed to be equal to 0. And so I can factor n plus 1 plus r out, so I get 4 times n plus r plus 3 times n plus 1 plus r times a sub n plus 1 is equal to 3a sub n. And so that a sub n plus 1 is equal to 3a sub n divided by 4 times n plus r plus 3 times n plus 1 plus r. And so that's going to be my recurrence relationship, and I'll have to do this twice for the two different values of r. Okay, so let's go ahead and do this. So, fresh sheet of paper, two possibilities. Case 1, r equals 0. If r equals 0, then that gives me that a sub n plus 1 is equal to 3a sub n over 4n plus 3 times n plus 1. And that will be my recurrence relationship if in the case that r equals 0. I can also shift this, so I get for a sub n is equal to 3 times a sub n minus 1 over, if I replace n by n minus 1, I get 4n minus 1. And then n plus 1 becomes n. So there's my recurrence relationship for the case that r is equal to 0. Okay, now this can actually be written in closed form. So we get that a sub 1 is equal to 3 times a sub 0 over 3 times 1. Then a sub 2 is going to be equal to 3 times a sub 1 over 7 times 2. And then plugging back here, I get 3 squared a sub 0 over 7 times 3 times 2 times 1. Continuing, a sub 3 will be equal to 3 times a sub 2 over 11 times 3. So that works out to be 3 to the third times a sub 0 over 11 times 7 times 3 times 3 times 2 times 1. And so it looks like the pattern is going to be that a sub n is going to be 3 to the n, a sub 0 over. All right, the number that appears here is going to be 4n minus 1. Then I descend by 4s until I get to 7 times 3. And then the part that's left here is n factorial. And so that is my closed form expression for the nth term of that series. So that gives me that. Okay. So one other thing, if n equals 0, what happens? If n equals 0, I would get one on top, and I would get something down here in the bottom that isn't a sub 0. So the pattern doesn't quite work for n equals 0, so I have to write that out separately. So we get that y of x is equal to summation n equals 0 to infinity, a sub n x to the n. So that's a sub 0 plus summation n equals 1 to infinity of 3 to the n times a sub 0 over 4n minus 1 down to 7 times 3 times n factorial x to the n. And of course, the a sub 0 can factor out. 1 plus summation n equals 1 to infinity, 3 to the n, times x to the n over 4n minus 1, descending by 4s to 7 times 3, with the extra n factorial on the bottom. And so that is the closed form solution that corresponds to r equals 0. Before I let this go, let's talk about how this could be programmed in Excel. So this one's not so bad. It's fairly short. So if we have A, B, and that's row 1, 2, 3, 4, 5, and so on. Okay, a sub 0 would go here. That's the 0 term. So a sub 1 plus 1, and then fill down. Then to program this would be equal to 3 times the previous term divided by n times 4 minus n, or 4 times n minus 1. And so that's what I would put here, and then that would fill down, and then I can get the coefficients. So that's how the Excel could spit out the coefficients. This one is actually sufficiently uncomplicated that I can actually figure out the closed form expression. Okay, that's 1 down, 1 to go, because that's r equals 0. Let's now look at r is equal to 1/4. Okay, let me change paper for this. For r equals 1/4, we come back to the original thing that we had up here. So if r is equal to 1/4, that would mean that a sub n plus 1 is equal to 3a sub n times 4 times n plus a fourth plus 3 times n plus 1 plus a fourth. And that's certainly a bit of a mess. Let's see if we can improve upon this. If I shift the index, a sub n would be equal to 3a sub n minus 1 over 4 times n minus 1 plus a fourth plus 3 times n minus 1 plus 1 plus a fourth. All right, what happens? 3a sub n minus 1 over. So here I have 4n minus 4 plus 1 plus 3. So all that cancels, leaving me 4n. And what's left is going over here is going to be n plus 1/4. So 3a sub n minus 1 times 4 times n plus a fourth. And that can be written more simply as 3a sub n minus 1 over n times 4n plus 1. And so there is my recurrence relationship for this one if I have the case r equals 1/4. Now again, this one is sufficiently simple that we can work out the closed form expression. A sub 0, a sub 1 will be equal to 3a sub 0 over 1 times 5. A sub 2 will be equal to 3a sub 1 times 2 times 9. Then plugging a sub 1 here, I get 3 squared a sub 0 over 2 times 1 times 9 times 5. A sub 3 is equal to 3a sub 2 over 3 times, plugging in n equals 3, I get 13. Then plugging in a sub 2 into here, we get 3 to the third a sub 0 over 3 times 2 times 1 times 13 times 9 times 5. And so it looks like that the pattern is a sub n is equal to 3 to the n, a sub 0 over n factorial times 4n plus 1, and then to descend by 4s until I get to 13 times 9 times 5. Okay, and then so that means that y of x will be equal to summation n equals 0 to infinity a sub n x to the n plus r. So the r this time is 1/4. So the 0 term is separate, so I get a sub 0 times x to the 1/4 plus summation n equals 1 to infinity of 3 to the n a sub 0 over n factorial 4n plus 1 times 13 times 9 times 5 times x to the n plus 1/4. And again, the a sub 0 could be factored out, so I have x to the 1/4 plus summation n equals 1 to infinity 3 to the n x to the n plus 1/4 divided by n factorial times 4n plus 1, descending by 4s till I get to 13 times 9 times 5. And so that would be the closed form expression for the second solution. Okay, so let's see how we're doing on the problem so far. Find the recurrence relationship for the coefficients. Done that. Describe how a computer program can do this. I did that for the first case. I haven't done that yet for the second, so let's go backwards for that. That a sub n is equal to 3a sub n minus 1 over 4 times 4n plus 1. So to do this as a computer program in Microsoft Excel, so a, b, rows 1, 2, 3, 4, again starting on 0, and a sub 1 plus 1 to fill down. Now the first term goes here, a sub 0. Each subsequent term is going to be equal to 3 times the previous term divided by n times 4 times a sub 2 plus 1. And then if I fill that down, that would produce the coefficients. Okay, so that is how the computer program could compute the coefficients. We found the minimum rate of convergence. We have found the closed form solutions for the coefficients. We've expressed both of them as series. The last thing to do is to directly compute the radius convergence of these two solutions. And we'll do that with the ratio test. Let's start with the one that I just got. And let's figure out the radius of convergence for this series. So the radius convergence, we'll use the ratio test, limit as n goes to infinity. Of the thing in the bottom is going to be precisely what I see here, 3 to the n, x to the n plus 1/4 over n factorial 4n plus 1 down to 13 times 9 times 5. Then on the numerator, everywhere I see an n, I'll replace by n plus 1 over n plus 1 factorial. Then replacing n by n plus 1, I get 4n plus 5, 4n plus 1, descending down to 13 times 9 times 5. Okay, so that's the limit as n goes to infinity of, okay, what's left? 3 to the n plus 1 over 3 to the n is 3. X to the n plus 5/4 over x to the n plus 1/4 is x. I have an n plus 1 factorial in this denominator. I have an n factorial in this denominator, so that leaves me n plus 1. Then there's a 4n plus 5 in the denominator that doesn't cancel out, but everything else does cancel out. Then as n goes to infinity, that equals 0. That's less than 1, and so this converges absolutely for all x. No matter what the value of x is, I get a limit that is less than 1. Finally, let's take a look at the first series, if I can find it. So that was this series that corresponded to r equals 0. Again, let's use the ratio test to see how this converges. Limit as n goes to infinity of 3 to the n, x to the n, over 4n minus 1, descending down to 7 times 3, with an n factorial to boot. On top, we have a 3 to the n plus 1 times x to the n plus 1, over 4n plus 3, replacing n by n plus 1. Then I descend by 4s. Then I have an n plus 1 factorial at the end. Okay, simplifying, 3 to the n plus 1 over 3 to the n is 3. X to the n plus 1 over x to the n is x. I have a 4n plus 3 that didn't cancel. Also, I have an n plus 1 that doesn't cancel with the n factorial down here. Again, that's equal to 0 for all values of x. That's less than 1. And so this converges absolutely for all x. And that confirms that the minimum radius of convergence was infinity, as we discussed at the top of the video. So that's all the parts of this problem for this regular singular point problem.